This is lecture number 7. And do you have any questions from the previous class? Okay, so at the very end we were discussing the phase frequency detector, and the last one which I mentioned was in the category of phase error detectors was D flip-flop type. So let me just detectors, and the last one was D flip-flop type. So see, D flip-flop also this one acts as like a 1-bit kind of phase error detection. So let's see how it works. And let me just say if this is your signal R and this one is signal V and the inputs are, you can say, sorry, let me just say here, or let me just put it as V here and R here, and this is output Q. I'm calling this as VPD. Okay, so it acts as a phase error detector in a way that if the rising edge of V falls anywhere between this region, you will get an high. Whereas if it falls, means if the same rising edge moves to, let's say, on this part, then you will get a low. So this particular phase error detector acts as a 1-bit of, so if I just say VPD, this will be high here, and it will actually, in this case, it will all remain high because the things do not change. So if I want to plot the input output characteristics of this kind of phase error detector, this is phi error. So it's like till the time you are between 0 to pi, it's all positive on this side, and it's negative. Negative means low here, which I am using -1 here. Okay, and if the phase difference gets more than pi, you can, from the characteristics, you can say it will be something like this. So this only detects whether you are lagging or leading the edge. Okay. So can you define the gain of this phase error detector when it locks? So it will obviously lock to something as a 0 phase error in this particular case. What is the gain of this phase error detector? So okay, let me just mark it more properly. So you see VPD with respect to phi error, and gain of the phase error detector is defined as D of VPD average with derivative with respect to phi error at the locking point. So what is the gain the way I have plotted? Huh? Yeah, the gain of this is infinite, right? So can anyone, means if you have seen it before only, I think then you can say, but I'm still asking, can anyone say that in the presence of noise in the system, whether the gain of this phase error detector changes? So let me put the argument in a more clear manner. So I have this D flip flop, okay, and let's say this is the input, or here I'm just changing the signals here, and I have a clock here, or here I can say clock is V, okay, and this is the output of the phase error detector. If R and V, they are both of the square wave signals, then you will see the input output characteristics the way I have plotted. Okay, now if in the same case, if let's say one of these signals is a noisy signal, So let's say this is a clean signal R, okay, and then I have the clock signal frequencies. Right now I'm assuming these are the same. So there is a noise in the system, which means I have a variation over here. Variation means when my edge comes as such. This is the window. And this noise depends on, it can be Gaussian, uniform, whichever way the noise contributes. So now, if I ask what is the average value of VPD, what is the way to proceed? So that R is coming as the fixed instant of time in absolute time reference, whereas the clock edge is coming early or late depending on the noise. Okay, so let's assume that in this case I am assuming the noise on clock is Gaussian, n of 0 comma sigma, with mean 0 and variance sigma. Okay, so if I want to define the average value, can you suggest the way? So output of my this VPD is positive 1 when my, so you see that if the means this is an absolute time reference, right? So now this is when I'm saying the locking point is at the absolute time reference. If there is any phase error between R and V, right? So this is the phase error corresponding to delta T. The same noise will be existing over here. Okay. Now, if delta T plus the jitter Tj is greater than 0, then it's positive 1, whereas it's negative 1 when the delta T minus Tj, sorry, delta T plus Tj, same variable, is less than 0. Let's use equal to on one side. This is third waveform is when V is offset by a certain delta with respect to R. Constant. This is the phase error. So what we are calculating is that if we are so if you see previously, right, we are having a very staircase, sorry, this is a sharp change at T equals to 0. If you are below 0, you are negative, you are above 0, you are positive. But think about it. If I am having a noise in the one of these clocks here, right, then whether you are below 0, below rising edge, or beyond beyond the rising edge, that depends on how much jitter is at the sampling point. Means the fixed offset delta T might be the same, but if the jitter is such that it can bring the rising edge of the clock before the data rising edge, right? So it will give you negative, and that is in the presence of noise. If there is no noise, the picture which I have drawn remains the same. So if I want, so all these things I am writing in an average. What is the average value of the phase error detector in the presence of noise? Okay, so yeah. No. So the thing is, the ranges are limited. So right now, what I am saying, considering it means what you are saying is right. If let's say the expression which I wrote, delta T plus Tj is not passing the pi phase error. That is a range dependent thing. Okay. We are right now. So if you look, the concern part is this. How can you use a phase error detector when you are having an infinite gain in the system. So yes, when you are at 5, then you will do the same. Discontinuity will be there. Okay. So this one I feel this is straightforward, which is Tj is greater than minus delta t and minus probability of Tj less than minus delta t. So if I show you the Gaussian, let me just curve here. So you see this is minus Tj, this is plus Tj, this is probability function PDF f of, write it as Tj, and this is Tj is the axis, sorry, oh yeah, this is minus delta t, this is plus delta t, and Tj is the x-axis. Okay, so the probability which we are looking means this term of the probability is actually is greater than minus delta t is your this region, right, which is same as 1 minus probability of Tj less than minus delta t. So this becomes twice. Okay. Yeah. Now you can means you can write it in terms of this in error functions and all. So if I just write this one, this will be 2 times now the all of this Gaussian expression will be there. So and this one is minus infinity to minus delta t. Okay. So if you plot this as an average value, you will get, you can work out this expression, you will get something as like this. Then you can approximate the gain of the phase error detector with a one linear expression, which is d of VPD average times dt or delta t. I can do it here with respect to delta t. You can do with respect to phi error. Okay, this one is minus 2. Then you have by root 2 pi 1 over sigma j and minus 1 delta t expression, and you have delta t square by 2 sigma square. I'm just doing a differentiation with respect to delta t, which will be, so this expression evaluated at delta t equals to 0 is root 2 by pi into 1 by 7. You can check if there is any factor missing. So you see this particular flip-flop, which is being used as a phase error detector in the presence of noise, has not like not infinite gain at delta t equals to 0, some finite gain. And what is this range of operation? Means, let's say if I just say it will not have a like a whole of the linear range, it will have a linear range in the limited part. Okay, and that linear range is actually dependent on your sigma jitter. It's turned out means that most of the time we take it as a plus minus, I think 2 sigma j as a approximated linear range of this phase error detector. Okay. So can someone tell about what is the benefit of using this kind of phase error detector? If we can do all this approximation, the gain in the terms is there is a linear range which is dependent on sigma jitter, and I can do all the loop calculations with this error, with this gain. Pardon? Yeah, so the gain is almost infinite without the and the jitter, without the noise in the system. But you can also say there is no system without any noise, right? If there is any system without any noise, I would like to use that in first place. Any circuit which you make will have a noise. So I was asking not is like what's the drawback. We know that the drawback is that this is having an infinite gain in the system. It's actually it is difficult to use it when you are trying to calculate loop parameters, because you can say the final sigma jitter is dependent on the loop parameters, right? And the loop parameters itself depend on the gain of the PFD, gain of the phase error detector, and the phase error detector is dependent on the jitter. So it's a cycle, means I cannot say I use this and I get the final thing. It's an iterative process. So beyond that means beside that, what is the benefit of using it? You should just see that this is one single flip-flop which can work at the fastest speed possible sometime. And it again depends what kind of flip-flop are you going to use. So the simplicity of this flip-flop is the reason why we use it as a phase error detector. And in PLL, this might not be, means this gain analysis may not be that useful because actually this doesn't not have a frequency detection capability. We will just see next the frequency detection capability, but this doesn't have a frequency detection capability. So in PLL you may not use it, but in clock and data recovery, in bang phase error detector, this is the, because you are operating at a very high data rate, you cannot employ any complicated circuit. Okay, and the analysis part of a single D flip-flop used as a phase error detector goes like this. Any questions so far? So this completes the part on the phase error detection. Now let's see, we have seen many phase error detectors, so let me just summarize the phase error detectors which we have seen. So the first one was multiplier, which has a sinusoidal characteristics. Next was sample and hold. Then we have exclusive XOR gate. After that we use two-state PD, then three-state PFD, and finally we had D flip-flop. Okay, so I have talked about all these things working as a phase error detection. I have not talked as a frequency error detection. So let's see what happens when you have a frequency error. So let me, okay, so let's say this is the clock wave, which is, yeah, I need to plot it a little bit. So this is the input clock. Okay, this one works a little bit better, was, okay, so this is the next one. T plus, okay, so let me just say R and V. Okay, so now in this, so this time period is T. Okay, so let's say f of R is equals to 1 by T, and f of V is equals to 1 by T plus T by 4, which is your 4 by 5. So the frequencies differ to begin with. Okay. Now, what is the phase error? I am still not using any phase error detector. I just want to show you what is the phase error detection to begin with. So here you see it means if they are aligned, it is close to 0. Here now the first time where you see this is the phase error detector, phase error at the input of the phase error detector. Then the next one, phase error detect, means it is with respect to all the rising edges of my reference clock. Okay, so the next phase error detector's value which I will get here is this, right? And the final means if you just go a little bit more, you will see. Okay, so let me just plot that too. So this one should be somewhere here. Oh, sorry. So this is T by 4, right? So now at this point, this is this. Right? So you see that the phase, if you are having a frequency error in the between the reference and the other signal, like the reference clock and the output clock, your phase error is changing from T by 4. In this particular example, T by 4 to T by 2 to 3T by 4, or not T by 4. So is the clock right? So this one is here, next one should get here, and then I think one clock edge is gone. No, this is fine, no? Yeah, so this is 3T by 4, and it will keep on increasing. Now, if I employ any of the phase error detectors which we have seen, so let's see what happens. And we know that the output of the phase error detector is integrated to get the frequency acquisition, right? So we have sinusoidal phase error, which is this is pi and this one is 2 pi, right? Then we had let me plot with another. We have another phase error detector which was having a gain like this. You have seen this one phase error detector, right? And this one was a XOR phase error detector. Then you have the two-state phase error detector which was like this. And then you have a three-state phase error detector which was like this. Okay, means these are the characteristics of VPD versus phase error. And because I plotted, so let me just make this as this was XOR or this was two-state PD? XOR. So this was your two-state PD, and this one was your three-state PD. Okay, so the example which I have shown you, the frequency error remains the same, means the reference clock frequency is higher than the output clock frequency, where reference is R and the, so let me just say this is reference and this is output. So reference clock frequency is higher than the output clock frequency, the phase error increases. So you are at T by 4, T by 2, 3T by 4. So you see that in sinusoidal, XOR and two-state PFD, for the same frequency, positive frequency error, you are changing the polarity of the signal. Right? So sometimes you may get positive, sometimes you may get negative for the frequency error, for the same positive frequency error. Okay, and I am going to average this frequency, mean whatever am I getting from the PD to get a frequency. So can you say that the average will be positive, negative, zero for different phase error detectors? It is hard to, I would say this very much depends on what is the frequency dependence. You may keep on getting positive, then you may get negative, and you may get more negative sometime. depending on what's the frequency difference. But if you look at an average of these, so let me just write VPD average for your sinusoidal XOR two-state PD. What can you comment on that? If the phase error detector output is this, and you're just integrating to get the frequency error. Huh? DC value will be means, can you confidently say that the DC value will be positive? Pardon? Can be positive or negative depending. And you're not means sometimes you're increasing the frequency, sometimes you're decreasing the frequency. Even when the case you have to increase the frequency. Always. Okay. So the only one which is having right now the same maintaining the polarity, I would say, rather than the proportionality all throughout the difference is two-state TFT. Okay. Pardon? Sorry, three-state. I'm sorry for that. So it's a three-state TFT which have the same polarity for the positive frequency error or for the negative frequency error. And the negative gain characteristics of PFD are like this. So the example, let me just come back to the same example. You have seen it has increased T by 4, T by 2 and 3T by 4. The next will be T, which is like close to 0. T is 0 means it depends how delta you are separated, and then it wraps it again, and again it will be the same thing. Okay, so if you consider, let me just come back as delta phi as 2 pi f in minus f out dt, right? Phase error, let me just say. We know that this phase error will keep on increasing for a certain frequency error, the positive frequency error, and after 2 pi you can reset it in this case. And you can see that resetting here very well. Your T by 4, T by 2, 3T by 4, again T, and then your edges are aligned in this case. Again you start from 0, T by 4 and those things. Okay? So the characteristics of the three-state PFD for a positive frequency error, you will be doing something, means on the gain characteristics, this is the path you are following. For the negative characteristics, you will be on this path. And now you are integrating always a positive value for a positive frequency error. So you will get a finite positive V control voltage to correct for the frequency. Okay. And another way to look at it is, this is on the phasor diagram. Let's say you are having this as FR and FV is greater than your FR, for example. Okay, so you have delta phi, or let me call this phi1 as error. After some time, the error increases, same FR and FV, and you have phi2. It will keep on doing, and then it will, so FR and FV, this is the total phase error, and again it wraps it back from the 2 pi. Okay, so what is the delta phi which it accumulates in each cycle is 2 pi times, pardon, can you just repeat again? Yeah, FR minus FV. So I'm writing here right now in terms of delta T. So that delta T will be your, this is again dependent on TR minus TV divided by, this is normalized to the lowest frequency, maximum of TR or TV. Means you can think about it, two periods, you are looking for a least common multiple in that sense, right? Okay, so the way I have shown you here, that your reference and output signal, right? In a first reference cycle, you have 0. In the next reference cycle, you have t by 4. Then t by 4, the final is t by 2, right? So what are you accumulating in each cycle? That is the time period difference between the two, right? And when will it basically wrap it again? After 4 cycles or 5 cycles, that is the least common multiple of the two time periods. Agree? So that is what I am writing it here. The delta phi per cycle is this. Okay, and in phasor I am showing that the phi v is moving with respect to phi r. Accumulating phi 1 means at the end is phi 2, and this is all the linear increment in each reference cycle. Okay. So does that make a sense for a frequency error detection? Yeah, one is constant. So you are always measuring the frequency of one signal with respect to the other. So the one, so okay, let me just. Yeah, I mean, this again, I have not yet put the loop here. Okay. So when you are when you are basically applying this phase frequency detector inside a loop, so now all these things are happening simultaneously. So the thing is, you correct for, let's say you got a t by 4 error, you correct for that. Okay, the next time it will not be t by 4, it might be, let's say, t by 8. So that will happen when you are closing the loop. But if I am looking for the characteristics of the phase frequency detector itself in an open loop, this is the way it will work, right? So the next thing is, what is the gain of this phase frequency detector? Okay, which is a little bit, so let me, any questions so far on this? Okay, so gain of frequency, I will call this as a frequency detector itself, because phase PFD we have seen the gain with respect to the phase error. Okay, so in the same example, let me start plotting it here. So let's say if this is the case, the R and V, okay, then when your R is high, you will, so now I am using a PFD output which is up and down. Okay, let me plot it separately, it's confusing here. So it's slightly away. Okay, this is R, this is V, up, down. So this is a PFD output, okay, and down is just a pulse right now in this case. Do you get this thing? Okay, this is for when I use a PFD. So you know the up and down signals. Okay, now V average of FD. So how can I proceed on this? Now averages means you can find some periodicity in the system, and you can average it after in the periodic period. So what I mean to say here is, in this example, you see that this output of this particular PFD will not be periodic in one cycle, right? It is periodic in some number of cycles. So I have to calculate those number of cycles. How to do that? So let me just say, if I accumulate delta t in one period, that is delta t by t, the next time it will be 2 delta t by t, right? And hence it goes on. After that, at one point, it will be n times delta t by t, and then it resets, right? Is that clear? So this one will be delta t by t. So now, when I'm writing this delta t by t, this average is delta t over t is equals to v of up minus v of down average over, sorry, this is the average in one reference period, right? In this example, in the first reference period, I can say that, right? So this one will be 1 plus 2 continue to n, and I think this everyone knows. This is n into n plus 1 by 2, right? Now, when does it wrap? It wraps when n times delta t is equals to t. Okay. So this n times delta t equals to t, what it is, so this term itself, let me, sorry. This term goes away, right? So I have 0. So back again, 0.5 plus 0.5 times delta t by t. Okay. Does it make sense? Huh? No, divide by 2, right? Yeah. So this one will be 0.5 plus, now what is delta t? Delta t is the time difference between the reference and the output. And I am, so this, now you can say the delta phi per cycle which I am using, this is coming from here. Okay. Any question? So I have this one as TR minus TV. I'm using it in this manner. So I have 1 minus 0.5 TV by TR. And this is, you can say that I am assuming that TR is greater than TV, right? If I consider TV greater than TR, then I have to consider the up minus down signals properly, and then this will invert. This TV becomes TR, TR becomes TV. Okay, which is 1 minus 0.5 times FR by FV. So in this particular, the way I have written here is TR is greater than TV. That means F out is, so yeah, this is little bit, so TR is reference period. Okay, TV is your output period. Okay, if delta T is equals to TR minus TV, that is TR is greater than TV, I am assuming here, right? In that case, do you think the up signal will be high or down signal will be high? What I have shown here is your actually TR is lesser than TV, right? So in that case, your down signal will be high, right? So the average value which you will see is actually negative of what I am calculating right now, right? Yeah. Here it should be. Yeah. It should be what? Wait a minute. Did I 30 by T is 1, N is equals to, yeah, okay. So, sorry, we can work it the other way. This one will be N plus, do you mean to say this? TSP up or down, N plus 1 by 2, 5. Okay, so this one is T minus, let me just write it as, okay, yeah, I think you're right. I'll verify this one, but just put it here right now. Okay. This one is, let's say, TR and TR minus T. Yeah. So the thing is this, when you are averaging for a VFD, right, it is not periodic with one period. So you cannot take an average over one period. So I am averaging over whatever periodicity exists in this output waveform. Okay, for that I am using these terms. Yeah. No, so you need to do the entire average. Yeah. Yes. So you mean to say this? Let's see this. Okay. So this one is divided by n. This expression is right? This one. So let me just try it here. So delta t. Now this one will be, so that is gone. So I have 0.5 into 1 by n plus 1. This, which is equals to 0.5 times 1. Now 1 by n is delta t by t, right? So you can say I was making two mistakes and getting the right expression. So this is 0.5. Now 1 plus, does this follow? Right? Which is 0.5 plus, sorry, this one is 1 minus 0.5 t v by tr and 1 minus 0.5 fr by fv. Okay, but you pointed that out. So this expression turns out to be little, I mean the gain will turn out to be non-linear if you do the whole analysis. So this is one part of it. And here I considered that your TR is greater than TV. That means the reference is greater than the output. Okay, which means in the case of the PFD output, you will have the down signal high. Okay, so which will be, so if I write it in terms of in the real expression of V of up minus V of down average, that will be equals to negative of this. I just did this here, but you can calculate properly, which is equals to 0.5 FR by FV minus 1. Okay, and this is for the, on the other means, this is for the expression when your FV is greater than your FR. You can work out the same, this one I am writing it slightly, VFD average, which is V up minus V down average, okay, is this. Then the other side of the expression is V up minus V down average is equals to 1 minus 0.5 FV by FR when FV is lesser than FR. This can be work the same analysis which we have done. Okay. So the transfer characteristics of this, so let me just plot, this is your FV, this is VFD average, right? There is a point where your FR is equals to FV, that is delta F equals to 0. So I'm just plotting these two, and these are two different expressions. Okay, so let me just plot when your FV is lesser than your FR. That is basically in this region. FV lesser than SR, FR is this region, right? And this one is linear. If you see, this is a linear expression. Okay, so this is something, let me just like this. And this one is 0.5. Okay. Then on the other side, on the other side of the expression, you see this is a inversely proportional to FV, which is something kind of, okay. So these are the characteristics of the phase frequency detector when we are using it as a frequency detector only. This is the frequency detection part. The phase detector part, you have seen the characteristics. Okay. Now the thing is, how do we use this frequency detector in the PLL? There are multiple ways. So let me just show you the first one. This is, so now I can say the phase frequency detector is detecting the phase error also and frequency error also. Okay. Then I have the loop filter, and what do we need in the loop filter for for it to detect the frequency? Type 1, type 2, or what? Pardon? Integrator. So we have to use an integrator in the loop filter and a VCO. So this will detect your frequency and phase both. So let me just say F in and F out. This is the first one which you can think about once we know phase frequency detector. The second one is that you can use a separate frequency detector just to detect the frequency. You can use a separate loop filter for the frequency detection, and at the same time you can use a phase detector. Now here it can only be a phase detector. You do not need to use it as a frequency detector. Another loop filter, and you have a VCO, and the output of the VCO goes here, and it also goes to the, so this is the VCO output, and the same reference goes to both of them. Okay, and this part of the loop itself as such is called FLL, frequency lock loop, and the other part of the loop is called phase lock loop. Yeah, we will come to that. So the topic, the way we went was we basically detected the phase. We say there is no frequency error. We detected the phase error, but we find all the phase error which we are detecting, they cannot be used if you are having a frequency error. So we found one phase error detector which can detect the frequency also. So that is the one PFD which we use, 3-state PFD. But the thing is, I can still split the loop into two. I can say I am doing only frequency detection in one loop and phase error detection in the other loop, right? But can you point out what will be the problem if I use two loops which are trying to control the same thing? I gave the answer, but I am just yeah. So what can be the problem? Yeah, yeah. No, so okay, let me clear to your question, get to your question. So you say, let's say if your frequency detection has been done, frequency is locked, and my phase error has not locked. Phase is not locked. If you are using the phase detector, phase error detector, which we have used shown so far, you do not need a frequency. So let me put it this way: you do not need a frequency detector loop to get the phase. Okay, but now when you are, your phase lock loop is working to get the phase, to recover the phase, in that time if your frequency changes, because you are controlling the voltage, so you are controlling the frequency. So if that time the frequency changes, whether your FLL will come into picture or not, I mean it will get activated, right? So that particular thing is the same thing, like the two loops are controlling the same thing. So I can say if I make my FLL as a very low bandwidth loop, that if I am changing some frequency quickly on the phase lock loop to recover the phase, I do not go and change the frequency. So the bandwidth of the two loops are actually used to slow or fasten one of the loops. If both the loops are trying to do the same thing with the same bandwidth, then you will have trouble whether you lock or not. Means you try to change the phase, you try to recover the phase, and in that you change the frequency, so then the frequency gets changed. So that thing needs to be monitored. So that is a kind of a problem with the, if you are trying to do the dual loop architecture. But this is also used quite often depending on application. Okay. Do you have any question? The drawback of this is that first thing is it cannot detect the frequency. Which one? No, 3-state can do it. So the thing is, when you are operating, so one other thing is this way. If you are operating it as a frequency detection also, right? The linearity of these things will come into picture, or the phase frequency detector itself. Means theoretically there is no limitation on it. You are talking of the PFD or talking about D flip flop one? Okay, so last PFD or PD? PFD phase. Okay, so what's the problem there? Mm-hmm. So, okay, let me rephrase the question as such. So, if you are asking if the inputs to the PFD are sinusoidal signal, what will happen, right? So, if the inputs are means I have never designed it that way, but I think if you use a CML logic, current mode logic, with the sinusoidal signals as the input, right? Then your PFD input to output characteristics will also turn out to be similar as it is for the CMOS logic levels. Means I think we have seen, right, you do a digital XOR, right, or you do an XORing with the sinusoidal signals with or continuous wave signals in a CML logic. You will get the same output, but the swings are limited there. Okay. And the other thing is that the PFD which you are seeing here, the output of the PFD is still in time. We are processing this time information later. So when you do a separate frequency detection, you may not be in a pulse width modulated manner. You do in a, so just for an example, I can say if I want to detect a frequency of 1 gigahertz, right? I have a 1 megahertz reference. Okay, and I can very well say how much am I counting in the one microsecond for 1 megahertz, and that will still give me a frequency detection, right? So those kind of frequency detectors also used. The easy thing is that you can use that frequency. So okay, so now when you are controlling your VCO control voltage only with the PFD, right? Whatever loop filter you are using, that loop filter has to be decided by both for the frequency and phase error. How much? So just for an example, let's say this is VC1 and this is VC2. Okay, in case the upper loop was not there, then the output should be like VC1 plus VC2 for a frequency detection. Means VC1 coming from the field, VC2 coming from the frequency. So the loop which is operating as a for the phase error detection, for the phase recovery, right? That also has to go for the frequency recovery. Then VC2 has to be given by the loop filter for the phase. So can you do that easily? That's a question. Whereas I can separately control the thing. A quick example will be, you know, ring oscillator or no means or I. So ring oscillator is simply like this. I control the current source of the ring oscillator, right, to control the frequency. That's the easiest part. Now, if I do a PFD which governs the whole frequency of this oscillator, and frequency and phase both, that means, let's say if this is a 1 milliampere current, I should be able to vary this 1 milliampere current completely. Whereas if I split this, let's say if I come within, I have a 0.9 milliampere current coming from my frequency detector part, okay, and only 0.1 milliampere coming from my PD part, I can vary the gain, I can have a different loop filter control. You do not get limited by the frequency acquisition range if you do frequency detector and phase detector independently. We will see this thing when we come, it's like more of a wide band frequency detection, wide acquisition range, low jitter, wide bandwidth and all those. Okay, so let's stop here.